Hey, everyone. I know everybody is a little tired and eager to start the reception, but we have one more talk left, so please make your way back to your seats. We'll give everybody a second. So for the last talk of the day, we have Baron Schwartz, who he's the CEO of a company called VividCortex, which is a database performance monitoring management system. It's a SaaS product that works with a lot of time series data. I first met Baron back in 2014 in early May at Monodirama. So this is like when InfluxDB was maybe like 6 months old. He was working on VividCortex. And I was really interested. Baron has a lot of opinions about time series data and about analysis. And he also has opinions about anomaly detection, which I somewhat agree with. So when I emailed him to ask him to come speak at this event, he gave me a couple of ideas, and one of the ideas he gave was that he would kind of like rain on everybody's parade about anomaly detection, right? Anomaly detection is supposed to be this holy grail, this magical black box that will tell us where problems are, where they're going to be. And I'm always kind of like the old man in the room that wants these kids to get off my lawn. I don't believe in it. So when Baron had this talk idea, I was actually very excited. So I asked if he could come present it. So Baron.
Thanks, Paul. So that's basically my talk. Get off my lawn, you anomaly detectors. But seriously, there is a place for anomaly detection, and then there's a lot of places where it shouldn't be. And I've got some more stories about trying to build some stuff myself. Oh, I forgot to ask, is there like, a gift that we can give to somebody who figures out the nerdy joke that's going to come towards the end of this? I'll just seed that thought now if anybody has like an InfluxDB hoodie or something to give away. So let's actually, Paul gave a great introduction of kind of some of the background about how I got into this stuff. I founded VividCortex in 2012 and started slurping in a lot of time series data. It's really high cardinality. It can be tens or hundreds of thousands of series per second from any individual database server. So what we do is we measure the database query traffic. So we really focus on the workload of the database and not things like status counters and cache hit ratios and things like that, but really just what is the database working on, which is queries, and measuring and characterizing that. And it's a high cardinality, messy, really big data, whatever, quote unquote, hashtag workload. And because it's a really big, messy workload, there's lots and lots of time series along different dimensions, and it can be really hard to make sense of those kinds of things. So, and we measure it at really high frequency. We measure every query, and then we collapse things into digestible bits, and then answer questions like, what are the most frequent queries, or the most time-consuming queries, which queries are causing the most errors, those kinds of things. And immediately, people wanted to have anomaly detection. So a really frequent request that we get from customers is, but couldn't you just tell me when important queries have unusually high latency? And it sounds so reasonable, right? And also around this time, there was some significant thought leadering at the initial early Monotiramas and velocities and so forth, and there were some companies that were kind of making their mark and staking their whole reputation and branding and marketing on anomaly detection and how it was going to solve all kinds of problems. And I found something quite different. So I'm a little bit more like John Allspaw, who says it's an unsolvable problem. And there actually is some mathematical theorem out there that says that computing the right answer is actually uncomputable. So anomaly detection and forecasting and prediction, to do it right is an infinite computation problem. And so you have to accept that the best you're going to get is some approximation, and then you can kind of back into things from that. But more on the human side of things, John's point in his open letter to monitoring companies, which is a blog that I copy-paste to somebody probably every 2 weeks, is that a monitoring tool isn't supposed to just give answers. It's supposed to be almost like an extension of your team. It's supposed to be something that you can go ask questions and include relevant snippets and have a conversation. Actually, in the end of that blog post, he says, I'm going to choose your monitoring tool the way that I would hire an engineer, or something along those lines. So his opinion is that it's unsolvable. So that's one piece of skepticism. And then there's the Google SRE book, which has a chapter on monitoring distributed systems, and they don't really go into this in very much depth, but it seems like even at Google scale, where you would often think that, certainly if anomaly detection is useful at Google scale, it's got to be useful, right? And they're actually kind of saying the opposite. No, as we've grown really big, we've actually simplified and we've biased more towards small and simple monitoring solutions, and then post hoc investigation of what our monitoring tools will find for us. So this magical, like the monitoring tool is going to magically automatically baseline to detect and tell us when there's something that we should care about, doesn't seem to really work very well. But then there's the vendors, right? And there's still, some of the vendors that were, Gartner cool vendors and challengers in the quadrants and all of those kinds of things 3 or 4 years ago are dried up and blown away. Some of them are still out there, and they're still talking about how it can be somewhat of a silver bullet. So we don't need to name any names because, if it's an anomaly detection vendor, they're all saying this, right? That's what they do. And I don't want to criticize any particular one. What I want to talk about today is just a little bit more realistic, like what is it, how does it work, what's hard about it, and what are some successful use cases that I've actually found for it. And then some war stories. There's more war stories for me than successful use cases. So anomaly detection gets called a lot of different names, and it tends to be as the buzzwords of the day. So back in 2010, big data was the buzzword of the day, and people couldn't get enough of big data. Then it turned into machine learning, and various companies have called various things by different names, artificial intelligence, things like that. So a lot of these kinds of things are simply anomaly detection, and anomaly detection itself is actually predicting and forecasting. Or an extension of predicting and forecasting. So really when people talk about anomaly detection, they're talking about, I want to find something that's not normal. The assumption is that systems that have not normal things are going to be interesting and or problematic. And normal is, because we're building things with computers, normal has to be somehow formally defined. And it usually turns into a mathematical model. And I was really glad about the modeling time series in R talk that we saw earlier today, because that is what this stuff boils down to, right? It boils down to a bunch of mathematical notation and all of these ARIMA models and exponential smoothing and double exponential smoothing, and that one doesn't catch enough, so we have triple exponential smoothing and all of those kinds of things. So that is that, ultimately it gets boiled down into some equation somewhere, and that ends up being a proxy for what is considered to be normal. But there's lots and lots of assumptions that get baked into that. And then what you do is you use that model, which is supposed to define how things normally behave, to predict. So you train the model on past data, and you say, in the case of monitoring, the assumption is that you're going to look at data as it comes in and say, is this data point anomalous? And that question is really answered by kind of flipping it around and going, use the past history to build a model of what looks normal, take a new data point, predict what that ought to be, and the confidence interval or the range of values that you feel represents normal. And if the new data point falls outside of that, then we have an anomaly. So this is what kind of gets used over and over and over again. And it's funny that it seems to almost, even without any knowledge of anomaly detection, this is kind of where an engineer's mind goes. I mean, certainly mine did. There were a lot of things that I didn't know about, and I sort of invented, and then people were like, oh, you've just reinvented, control charts from, from operations theory, and you should go read about that. And I'm like, well, if I had only known those words, I would have saved the last year of kind of reinventing the wheel. And I found again and again and again that because these things feel kind of intuitive that this is the right solution, and because we're all engineers, we sort of reach for those same solutions, but they don't really work very well. So that's going to be part of what I hope to rain on the parade here today. So there's lots of unconscious biases in these things. A little bit of statistics. You feel like 2 sigmas outside of the away from the mean is maybe a good proxy, or 3 sigmas away from the mean is a good proxy for what's unlikely to happen. So unlikely immediately becomes a proxy for abnormal. And you have this assumption that somehow you can build a model where if the data is not normally distributed, the nice bell curve, then at least the residuals are normally distributed. And if that's an unfamiliar term, the residual basically means the prediction error. So the idea in anomaly detection is generally that you can build some model of the process that's happening and then use that to predict what the next data point is, measure the distance between those, that's your error. And then if you draw a histogram of those errors, then the assumption is that it's a bell curve. And then you can use your sigmas to figure out, out on the tails of the bell curve, those things should not happen very often, right? So there's tons and tons of assumptions encoded into that, and a lot of those things don't turn out to be true. And so you've probably heard things like, the normal distribution is a fallacy, monitoring data is not normally distributed, but then the person who knows statistics goes, but the data doesn't have to be normally distributed. You just have to have a model, and then you get the residuals, and the residuals can be normally distributed. And you look at that stuff, and you're like, the residuals do look normally distributed, so it should work, right? And then you're really, really surprised when it doesn't work at all. So this distance between theory and practice turns out to be pretty large. So we have these things like, what is the model that produces this, that produces the systems that are going on, produces the behavior that's going on in our systems. That turns out to be essentially impossible to model. So we fall back to some things like the future is likely to look similar to the past. I mean, that's the simplest weather forecast model, is that today's weather is likely to look a lot like yesterday's, right? And that turns out to be surprisingly accurate to a first approximation. So a lot of models are essentially that kind of a thing, finding some sort of a central tendency, projecting it a little bit. The next level is finding a trend, all those kinds of things that the earlier talks talked about. Another incorrect set of assumptions that I found not to hold true is that in addition to this bias that the model is actually going to work well and that you won't get many inaccurate predictions. Another bias is that inaccurate predictions aren't really that harmful. Accurate predictions are really, really helpful, and I don't think that's true. My observation has been that that's not true. So, but every anomaly detection or forecasting or baselining or whatever product has a picture that looks like this. This one's from Datadog. Datadog has a team of data scientists. This is incredibly good quality work. What they're doing is really, really good quality. But it a lot of times it's sort of from the consumer's point of view. When I go and, when somebody goes and a person who's maybe making a purchasing decision or making a decision to deploy a technique or to use a technique, goes and looks at a web page, they see a picture like this and they get a good feeling. And the good feeling is like, Datadog and their team of data scientists, or whoever in their team of data scientists and their algorithms, can really do a good job of predicting. And yes, they can when the data looks like this. But there's sort of obvious questions about whether your data, what kind of use case are you going to be using this for, and does your data for that use case actually match this? So if we look at some of these things, it turns out that anomaly, the definition of anomaly as being something abnormal, is not very useful. A better definition of anomaly, rather than something that falls outside of shaded bands, is actually something that I need to do, something that I need to take action on. And people think that they want to know when something falls outside of the shaded bands, but they really don't. When they start getting alerted on things that fall outside of the shaded bands, they start regretting it really, really quickly. So let's talk about some of the reasons why this is hard. I've kind of described the situation, but let's talk about the reasons why. So number one, real-time data often isn't real-time, or real-time anomaly detection often isn't real-time. You may be getting your data in real time, but if you want to act on it in real time, you have to look at the noisiness of getting data in that granularity. Because when we look at it across the large time scale, it looks like the picture that I just showed you. But when you look at it in fine resolution, it looks like absolute, a white noise generator. And this is just a picture of a white noise generator. So it's only on these long time scales that the data actually looks like something that we can draw nice bands around in the general case. And this is a quote from an anomaly vendor. You should check your KPIs several times a day. That's not real time. So if you had this idea that you were going to be notified, a second or 60 seconds or 5 minutes after something went off the rails, if you're looking at data in that granularity, if you're looking at that frontier of the data now in sort of operational human real time, let alone like financial trading real time, it is incredibly noisy and very hard to model. And you find that your systems are quote unquote abnormal all the time. And that's where the high rate of false positives comes in. So modeling the data on the right is significantly harder, and I would say in most cases it's probably nearly impossible, as opposed to modeling the data on the left, which it's a daily trend. If something goes askew in that trend, and several hours or half of a day passes, and it's definitely outside of the bands, that's several hours or a day that's gone by before you've gotten your real-time alert, right? This cost-benefit trade-off, it's highly asymmetric. So the idea, or the kind of implicit assumption, is there's not going to be that many false alarms, and the cost of a false alarm isn't that high, and there's probably not going to be that many false negatives, and a false negative probably isn't that high cost. But getting one alert about something that is wrong, man, that's worth its weight in gold. And that's wrong. That's upside down. The truth is that, again, there's all of these wacky things that are happening in our systems all the time, and most of them are not actionable. They're literally not even diagnosable. It may come from a solar flare, or it may come from just, like somebody twitching or a deploy or something like that, something that's in the normal course of business, and there's nothing for you to do about it. But on the other hand, if you build these models of your systems, even if you work really, really hard, you get lots and lots of indications that something abnormal happened. So the cost-benefit asymmetry, in my opinion, is exactly the reverse of what sort of, as engineers, we are kind of genetically wired to think, I guess. Just because we don't think in probabilities very well, it's really unintuitive. And alerts that come in that are non-actionable immediately turn alerting systems into a Gmail filter into the trash bin, disengagement, pager burnout, people's disrupted attention. Things very quickly spiral until that product or project becomes shelfware. Even things that seem to have initially a lot of enthusiasm. I haven't really followed up on this, but I remember probably back in the 2012 timeframe, Etsy had a couple of anomaly detection things. There was Kale and there was Skyline. And initially, they seemed to be really excited about this and showed some success stories at Velocity Conference and some things like this. But then when I talked to them sometime later, it hadn't really ended up helping a lot. And I think people kind of soured on it. I should follow up and check on that, but I think that's pretty much what happened. The fourth problem that I've seen is that the results come out of a black box, and that black box is not interpretable. You can't tell what it means. The data is highly digested, and you would have to retrace, and it is surprising how quickly you end up 6 or 8 degrees of separation of processing from the original inputs. So you'll take an input like CPU, and it'll go into a model that has 6 or 8 steps, and one of those steps has like a neural network of 1024, and one of those was selected as the winner, And so you're trying to audit, like, how did we get this answer? And it is impossible, even if you wrote the code. and to give you a sense of how difficult this is, even if you take something like an exponentially weighted moving average, which is super common, they're all over the place, and you encode its value as a metric and store that into your time series metric system, and then you get an alert off of that, and you go back and you're like, why was the why was the exponentially weighted moving average 1.83, some really long floating point thing? And you can't really reproduce that state because the exponentially weighted moving average has essentially infinite history, and so you would have to figure out when that thing was initialized. and replay maybe weeks of data to actually get to that point, to get to the same answer. And I've chased down this rabbit hole myself, and it's like, this thing was like, it's a floating point comparison, and it's, something out in the 17th digit comparison over the threshold that we set. And how did it get there? Because as far back as I go, I can't get that exponentially weighted moving average to actually reach that state again. Super frustrating and infuriating. And then if you look at the anomaly detection things, I mean, they're much, much more complicated than that. So you end up with this black box that you can't audit. And when you have that situation, and particularly when you're trying to assess whether something is actually actionable or not, is anything wrong? Or if something is wrong and you're trying to use anomaly detection stuff as input, it's really, since it's hard for you to reason about and you can't grasp it, you're in a situation where you're under a lot of time pressure. You cannot simply reboot things or whatever. There's high consequences for whatever you're about to do. There's high consequences for not taking any action too. And you have a hypothesis like, I think if we reboot this one, it may solve the problem. The risk, you're making all of these risk-benefit kind of calculations in your head, and there's a team of you doing that, and people are pasting things into Slack that are irrelevant or maybe relevant, and you're trying to sort out all of this kinds of stuff, and the clock is ticking and customers are suffering. And the last thing that you want is something that's hard for you to reason about. So this is why people ditch monitoring tools, and they go to SSH. They SSH into the damn server, and they start IOStat minus DX1, and they watch it scroll up the terminal because it's something familiar and more or less raw that they feel they can trust, rather than it's coming out of their monitoring system through a black box anomaly thing, and maybe with a time delay, and if how much delayed is it? And basically, it's a question of, are my tools going to fail me when I need them most? So when anomaly detection basically fails all of these tests, right? You're very far from the raw underlying data. And then the systems that we're building them on are highly dynamic. And I think that's a phrase that a lot of us have talked about. And it may feel like this is something that's, we're kind of hammering this and overstressing this point, but these systems can take weeks to train. And yeah, we all know that servers, quote unquote servers, might only have lifetimes of hours now, but surely, the service lives on, but it doesn't. Because in the course of weeks, you probably have released a couple of new versions to it. And so literally the underlying model that's generating the signals that comes off of it might not only, live for, from one release to the next. And even if the service is long-lived, you now have a service that's behaving totally differently. And the models and the parameters that are being trained from these things really need longer than that. I mean, if you think of the typical periodicity of those kind of long time horizon smooth charts that look nice with the confidence bands drawn around them, those things take a few weeks to initialize, because your period is, it's usually, your periodicity is something like, a 5-minute interval every 5 minutes for a week. So whatever, however many 5-minute intervals there are in a week, you typically have to have a few cycles of that to actually get some training data. And, by the time you release a new feature or change the implementation of something, you've destroyed your training data. There's other kinds of consequences, like if you have an anomaly detection thingy or vendor, and they're spitting out, or a forecasting vendor or library, and it's spitting out an answer, a prediction, you have a question about whether you want to store that or not. If you don't store it, then you're not going to be able to have a reference point for the past. So if you wanted to ask, like, a week ago, what did our prediction a week ago think that this thing was going to be? If you didn't store it, you won't be able to know that unless you go back and reconstruct it, which may require some non-deterministic amount of replay to get to. But if you do store it and you want to change or upgrade or improve the anomaly algorithms themselves, you can't do that without recalculating everything. So it's kind of a catch-22. And a lot of things like Prometheus and so forth can't really operate on kind of ephemeral, constructed on the fly anomaly confidence band predictions. You would have to actually generate a series and compare against that. That's not strictly true, but for the more complex models, it in practice would often end up being true. So it might have to actually be a real physical metric in metric storage, which has a lot of challenges. And that's a real war story for me, because I built one of those, and constant challenges with trying to get those things working right and upgrading and so forth. And finally, anomalies, or maybe not finally, maybe I have another slide after this about the problems. Anomalies themselves end up, unless it's a very sophisticated algorithm, they often end up skewing the forecasts. So if you have, some, traffic spike from when Michael Jackson died, for example, I remember some folks having a conversation with them around this. That traffic spike was enormous, and then their seasonality predictors and everything essentially predicted that there was going to be another traffic spike like that for some time going forward. So it actually skews what's considered normal going forward. So you can compensate for that, but then you've made your systems a lot more complicated. I did have one more. So the vendor hype doesn't really help here, because the vendor hype, I think, continues to largely ignore these things. And sort of talk about the benefits without some of the potential trade-offs. And I also don't think that it helps that buzzwords like machine learning are used when it's clearly just Holt-Winter's prediction. And getting the parameters right for Holt-Winter's forecasting is non-trivial. If you've ever tried to do that, even simpler ones, it's really difficult to pick the right parameters. So machine learning is a great way to pick the parameters, but let's talk about Holt-Winter's prediction with machine learning to choose the parameters instead of talking about machine learning, just because it's a buzzy trend word. Same thing for artificial intelligence and so forth, because it ends up creating social problems that go beyond the technical problems. So let's talk about what anomaly detection is good for, because there are some use cases that I've seen it be pretty valuable. Some of them are, and here's my golden hammer. It is not a golden hammer. So why do we want it? We want it because we have lots and lots and lots of data. And we can't make charts and dashboards and scroll through all of them. We can't even search through and make sense of all of our metrics if we're storing metrics about everything. In many cases, even using like one of the things that we implemented in VividCortex, which turned out to be really difficult to do well, was trying to find metrics that have similar shapes for people is essentially a search problem. Turned out not to work as well as we thought it would. But even with techniques like that, it's really difficult to consume the hundreds of thousands or millions of metrics that you might be getting off of your systems. But still, people want anomaly detection because they again have these, as engineers, they have these biases. As an engineer, I myself have this bias that this must be a solvable problem, it must be a tractable problem. And it doesn't seem like, from the 80-20 perspective, it doesn't seem like it would be that hard to get the 80% of the benefit. So what I've seen it be good for is really specific uses, where it isn't just like I've got 1 million metrics and I want to just throw anomaly detection at it and see what it tells me about my 1 million. Like, out of the 1 million, are there 3 that are interesting? That's not a good use case for anomaly detection. A good use case for anomaly detection is something like a very high-level KPI, like the number of signups in my app, or the web traffic, or something that is essentially you can pretty much count on, because it doesn't necessarily rely on the model of how your system is built. It relies on a population of user behaviors. that is, it's going to change over time, but it's going to be one of those kinds of nice things that we can draw confidence bands around over a longer time period. And it should be a large enough data set that you start to get the law of large numbers put to work, and filtering out, the outliers are going to be drowned in the average. You really want to be looking at a large data set so you can have a solid central tendency. And when I say you validated the behavior and you expect it to be immortal, I really mean things like application traffic on a large-scale consumer-facing web property, for example, where you expect that as many people are going to be reading the New York Times today as they typically would at this time on a Wednesday. That there isn't going to be like, another newspaper comes up and everybody abandons the New York Times. You would expect the New York Times' traffic patterns to be relatively durable to those kinds of events, and not really to vary much based on whether the New York Times adds a new cooking editor or something like that, right? So a large population that's probably going to be pretty slow to change. Number two, and here we're actually getting away from anomaly detection into capacity planning. So this is a forecasting and prediction problem, and a lot of the use cases, we talked earlier about Facebook Profit. That is, if I recall correctly, that one was mostly used for capacity planning. Netflix's Scryer is mostly about capacity planning and predicting how many EC2 instances they need to spin up just before they're needed, those kinds of things. Usually when you look into like the tech blog, we built our own anomaly detection at Twitter or something like that, they'll talk about, look, there was this thing that happened at Christmas and at the 4th of July and those kinds of things. And so my question would be, is that an anomaly? I mean, you pretty much expect that a bunch of people are going to be posting photos at Twitter at Christmas, Twitter photos of their families. I don't think that's an anomaly. If we get back to the definition that I advocated earlier of an anomaly as something that you need to take action on, do you need to take action on users uploading a lot more photos or tweeting a lot more? I don't think that qualifies. So I think, understanding seasonality and then forecasting and saying we should expect a lot of people to post a bunch of photos this Christmas too, do we have the capacity for it, is a valid question, but it's not necessarily anomaly detection. Number three, if you have a team of data scientists, and obviously there are companies who do, like Twitter is a great example, Twitter and Facebook and all of these kinds of folks, but most of us don't have a team of data scientists working, we don't even have one data scientist working 40 hours a week on any particular set of problems. And what that means is that if you don't, I think it's actually an anti-pattern that you should strongly consider not trying to do this kind of thing, because you need somebody to own this. Because as things creep, this thing is going to drift into bad behavior, and you need somebody who's actually going to be paying attention to it, care and feeding on a regular basis, and making changes to it and saying, our model and our assumptions have changed, and this is what we're going to go forward with. So I posted this on Twitter a little bit ago, and I just said, is this normal? And got lots of great responses, most of which were along the lines of, it depends, or you didn't give me enough context to tell, and those are all great answers. But if I'm looking at a metric, and it does something like it has 2 spikes here, and I don't know if that's normal or not, using any of these time series forecasting methods to look back way off the left edge of that graph, like 2 weeks into the past for this metric, and then draw confidence bands around the point that's in the parts in my viewport, would be super helpful. And that's a great use of forecasting and prediction methods. It isn't really anomaly detection, but just drawing some confidence bands and showing me, does this fall in the middle of what I would predict for this window of time, is super helpful. And actually, I did this. I mean, I went and grabbed a random metric from VividCortex. It's actually from our own production systems. This is a latency of a particular query. And I just looked at it on the 1 hour time frame, and I had myself have no idea whether this is normal or not. Then I looked at it on the 12-hour time frame. So, our 1 hour window is the 12th of the right-hand part of this chart. And yeah, I mean, it's basically pretty much normal. I mean, the spikes are a little bit higher, but they're in the same place. And when you shrink it down, you can actually see that over the hour, there's an increasing trend. I'll leave you to guess as to what back-end architecture causes that. What's that? Still in here? It starts with a J. I'm actually having a hard time guessing where you're going, but probably other people are. So yeah, I mean, if I took, a week or so of this data and then drew some confidence bands around the top graph, I wouldn't have to go look at 12 hours and try and kind of mentally bracket it and see if it looked normal or not. And finally, if I have a specific question, such as, is this normal or not, or those kinds of things, I mean, that's not the only valid question that I could ask, but if I have a specific question, then anomaly detection or prediction and forecasting can turn from a solution in search of a problem into a solution to an actual question. And I think just as engineers, we're predisposed. I hope I can speak for you and that this resonates with you, but I think as engineers, we're often predisposed to, ooh, cool, I could answer so many questions with this, when you don't yet have a question. So I think, it's good to resist that tendency until you have a question. I said finally again, and I'd forgotten that I added another slide here. So if you can't get it any other way, so I mentioned earlier that something that you might do, and I was kind of foreshadowing this slide, something that you might do is do anomaly prediction on a number of application signups. But what if it's better to actually do that a little bit better, a little bit different way? Instead of looking at application signups in isolation, look at the conversion rate of traffic to signups or something like that, a funnel conversion rate. And that conversion rate is probably very stable over time. You hope that you want to get it, trending upwards. But if there is a dramatic change in it, it's probably something that you can use a good old-fashioned static threshold against. And so you can often convert what you might think of is something good to use anomaly detection for into something that your traditional tools or metrics tools are very good at, and it's probably a better fit. Another thing that you can do is you can look at the relationship between metrics visually. And this is just essentially dividing one metric by another. There's 4 metrics on the left-hand side of this page. And a lot of times we talk about correlating time series metrics, and what we mean is sort of eyeballing them and seeing if peaks and troughs line up. But correlation obviously is a mathematical concept. And you can also just take those 2 metrics. In this case, I think I took the 2 middle metrics from the left-hand side, and I just plotted one of them on the x-axis and the other on the y-axis, and you can see the relationship between them visually. And you see that spike, the tableau in the middle is a set of outlying points scattered towards the upper right, and then most of the points are down towards the bottom left. You can also see that they appear to have different sort of relationships between each other in those different regions. And so that's information that's encoded in the relationship between those metrics that you couldn't get, and you don't necessarily need math for. Your eyes can tell you that really well. So as I conclude here, and we all go to our social and we start to drink away our problems, I think I've seen anomaly detection create more problems than it has solved, and certainly more than, as an engineer, I had sort of hoped that it would solve. So I'll tell you a couple of war stories. There's 2, actually make it 3 war stories that I can think of at VividCortex. So one of the features of VividCortex is it's a complex model of just 2 signals from a system that when you combine them with a couple of performance laws, can tell you whether the system is basically getting stuck trying to process things. So a lot of work is in progress and it's not completing. And over time, we've built a really reliable, very low false positive rate way to detect that, and it's based on a bunch of anomaly detection. The initial thing I implemented, and I was like, oh, this is going to be awesome, and then it turned out that it was significantly more complicated than that, and we had to put machine learning in it, of all things. So there's like, the stall detector that I built, which is a fairly simple machine with probably 6 or 8 steps, something like that, and a few moving averages and 2 signals and a couple of thresholds, turned out to be insufficient, and we had to build basically an ensemble of them. I think we do 1,024 or 4,096 of them or something like that. And we then ask them to tell us how well they are predicting on a real-time basis. And there's a selector that goes and listens to the one that is the most accurate. And so we had to build this really complicated machine. It's very difficult to audit and so forth and so on. And although when it tells us there's a stall, there is always a stall. You know, we've gotten it to the point where there's, if it says the system is getting stuck and unresponsive, it is. Still, that is very difficult. The war story part of this is it's very difficult for customers to put that into action because sometimes there's no smoking gun. The system is just getting unresponsive because it's reaching that boundary of operational stability and getting stuck. And there may not be anything that you can do about that. It may be, you know, a memory allocator, it may be a file system bug, it may be something internally. In our case, in the databases, mutexes are often a real problem. You know, as a user, are you going to recode the way that a mutex is implemented inside of MySQL or the way that pthread scheduling works inside of Linux? You know, no, you're not going to. And also, the interpretability of it is really challenging because people will see, you know, we assign a score of severity to each of these hiccups, and people will look at the score and they'll go, that one's 7.3 and this other one is 6.5. So how bad is it before it has to get bad? Where does that score come from? You know, should I pay attention to one that's over 5? And these are all questions that the answers, you know, there's a scientific and mathematical answer to it, but it doesn't actually answer philosophically the question. Ultimately, the real answer is kind of zoom your time range out so you get a lot of these things in a chart on the page, unfocus your eyes, and if the chart gets darker and taller over time, you have more of a problem. You know? So the individual stall events turn out to be kind of, I would say, you know, I would give this a 6 out of 10 score as effectiveness as a feature. And, you know, as a vendor and the CEO and founder, I'm not supposed to diss my project, but I just want you to know I'm not sure I would build it again. We also built traditional dynamic baselining, which lots and lots of systems have. You know, AppDynamics has it, et cetera, et cetera. We ultimately found that even though we were doing it on just only some very specific metrics that people had asked for repeatedly, like tell me when a particular very important query has an unusually high latency or starts throwing errors all of a sudden, we still found that people wanted to have it, but then after they had it, they didn't want it anymore. So we nixed it. We completely turned that off, and nobody has complained yet. So that it's gone. So this is a case where I think customers, you know, with the best of intentions, they don't know how to ask for the solution to their problem. They're asking you about a problem, and as a tool maker or vendor, you know, your job is to figure out the right solution to that. They'll often propose a solution to you, but you have to listen to the problem behind their proposed solution. And then somewhere along the lines, I forget where, so this is, if anybody gets the Baggins joke with anomaly detection, this is where I would love to have a hoodie to throw out to whoever gets this nerdy joke. Oh, we do have a hoodie. Anybody know why I named this project Baggins?
Bilbo Baggins is super annoying in the Lord of the Rings.
Bilbo Baggins is super annoying. That's, you know, you got Bilbo Baggins, right? What book is Bilbo Baggins in? He's the one. And we've got InfluxData socks, which I have a pair of, and I'm wearing my O'Reilly socks today. I'm sorry. We got a couple of good answers. The real answer is that the subtitle of The Hobbit is The Unexpected Journey. And and I thought I had this bright idea that instead of looking at the value of a metric, instead I would look at the amount of time between changes in the value, and if it changed at a time that I didn't expect it to, that would be an unexpected journey. And this was the worst spam machine I've ever built. It was horrible. It was horrible. So here's some books. to give you a sense, there's lots of books on anomaly detection. The one on the left is from some of the folks at MapR. Super smart. The one in the middle is from me and one of my colleagues. Super smart. Not me, the other guy. And the one on the right is the one that you should actually get and rate. And it's about how people interact with their systems and their teams when they're solving complex and confusing problems, which is what we think anomaly detection is going to solve, but turns out to be a very difficult solution for. So, all right, I will, wow, I think I'm right on time, right? So, I'm standing between people and drinks, right? So, ask questions at your peril, right? Happy to take questions, though. There's one over here.
As someone who's dealt with that Holt-Winter problem for about 10 years, you hit the nail on the head on a lot of those challenges. But I think the thing that you jumped to a conclusion is that when those confidence bands or those thresholds are violated, that you alert immediately. And what we found is that we don't alert. We then create events. Then based on the run book, you then solve that. Then we have a dashboard. It allows you to filter down. Because if you have millions of metrics, some of those you may want to understand what's abnormal, but you don't want to bother the individuals. And then only based on certain conditions would you then alert those individuals.
Yeah, that's a great point. So somewhere back in here, I was talking about context. And I had this thought in my mind, but I don't think I really, I didn't write it down or explain it. But I think recording when things go outside of the expected confidence intervals can be a really good thing to help you. It's essentially sort of a pre-marker for a search later. It's, at least in the systems that we have built, it would be basically infeasible to do this. It would probably triple the volume of metrics that we generate and the amount of data that we have to store on our back end. And it's probably also pretty difficult. We haven't tried to implement this yet, but probably pretty difficult for us to try and answer a question like that on the fly as well. Like, I'm looking at a 1 hour window and I see some spikes. Tell me what metrics looked like they were out of the bounds of normality during this. That would be sort of, let's go look at the last 3 weeks or 4 weeks of every metric in the system and train Holt-Winters or something like that, and then forecast during the time that we're looking on the chart right here, which, again, I haven't tried to implement, but I just sort of shudder in horror at the computational cost of that. So, but adding context, you would have to, I think to do this well, you would have to know what kinds of metrics are likely to be, fittable well with something like Holt-Winter's prediction, because there's lots and lots of metrics that don't even look this nice at all and don't have those kinds of seasonality. A lot of the monitoring data really does look like white noise, even on the day and week time scale. It looks really, really chaotic. So I think to do this effectively, my gut says that you would have to specifically select which things rather than just like do Holt-Winter's prediction on every metric that I'm collecting. Do you, by the way, I'd love to hear, do you do that for all of your metrics or just? Oh, absolutely. You don't do it for all of your metrics? So you've picked a subset that are like, these are sort of predictable and KPI kinds of things. Yeah.
I think what's more important is the fact that if you actually store information about what's abnormal, but don't necessarily alert about that, when issues arise, customers start complaining, you receive other faults, it gives you an avenue to pursue.
Yeah.
To understand where you need to investigate. Because with hundreds of thousands of metrics in a certain location, you may not know what to drill into. You may be wasting your time. So you need to speed up your operation.
He's got the microphone for you. I don't know how many people.
No, that was it.
Perfect timing.
All right. Okay. All right. Time to wrap. Grab me. Happy to nerd out on this stuff. So great to be here. Thanks.
I would like to.
Socks, anyone? Whoa. Sorry. Thanks, Paul.
All right, thank you so much, Baron. That was great. So I just have a couple of closing remarks, and then I will let you at the reception. Whoa, you're still on there. So first and foremost, You turned me off.
I have two.
All right. Okay, there we go. So first and foremost, I'd really like to thank all of you for attending. This is the very first event that we've done. I started this company just over 5 years ago. The very first commit on InfluxDB as a project was September 26th of 2013. So if you had asked me back then if I could have envisioned this event with this many people and these great speakers, there's no way. So really, thank you so much for coming. Thank you to our sponsors, Seek, Grafana Labs, AWS. So one thing I wanted to announce while I have the stage here is that we're already planning the next InfluxDays, which is going to be in New York City on February 13th. So as part of that, we are going to be sending a feedback survey via email, and we'd love to hear what you think of the event, what you think of the content, right? Because our idea on this program was, it was a little bit, I guess, adventurous, which was we didn't want to make it exclusively about influx. We wanted to make it really about this idea of solving problems in time series data. Problems in infrastructure, problems in algorithms and analysis, and problems in visualization and summarization for human consumption. So, for the next event, we may have more influx-related material, but we'd love to hear, does the format make sense? How is the content? What should we have more of? What should we have less of? Okay, so the reception is just going to be right over there. There is wine and beer and past hors d'oeuvres, and I want to thank AWS, who is sponsoring it. So have your first drink be a toast to them. Thank you very much, everybody.